Today we look at the self-adjointness, and then we consider self-adjoint ODEs. Okay, self-adjointness and self-adjoint ODEs that we are going to consider. Suppose we have two functions, or we can say two quantities u and v, and L is some operator that can act on these functions u and v. Okay. L is some operator. It may be a differential operator that operates on two functions u and v. And suppose we consider u into v, and L is an operator that operates on u. And if L u into v, if that is equal to u into LV, okay, L into L that operates on u, the function u into v, if that is equal to u into L that operates on v, then we say L is a self-adjoint operator. L is self-adjoint. Okay. So this is the idea of self-adjointness. Now suppose we consider, instead of such simple products like this, we are considering inner product. We are considering, what is it? Inner product. Okay. Inner product of u with v we are considering, and that is defined like this: u v, inner product of u v, that is integral a to b u of x v of x dx. Okay, that is the inner product of u and v. We represent it like this: u comma v bracket, or we can use this type of brackets like this. So both these are inner products. U and v are two functions. Okay, and it is given by this u comma v. This is equal to integral a to b. So a to b is the interval in which you consider this. So this is u of x v of x dx. So this is how we represent the inner product. Okay, this is the inner product of the two functions u and v. And suppose we have an operator acting on v, LV. Then this u LV, that is given by integral a to b LV v dx. So L is the operator that operates on v. Okay. Now, in this form, we actually write u LV. This is, we know what is ULV that we just defined here. This is actually, in this type of notation, it is L adjoint. This is L adjoint u comma v. So inner product of an operator L adjoint acting on u comma v. The inner product of LU or L bar u and v. Okay. So these two are equal, and if I have this L bar, the L adjoint, if that is equal to L, so what is L bar? That is the adjoint of the operator L. If this L bar, this adjoint, if that is equal to L, then we say it is self-adjoint. Okay, so this idea that we are going to use here, and we consider self-adjoint ODEs. Okay, we consider self-adjoint ODEs. So the self-adjoint ODE that we are going to consider is this. A differential equation, we have already seen differential equation like this, y double prime plus p of x y plus y prime plus q of x y that is equal to 0. So this we were considering such type of differential equations, and we are forming a differential operator out of this, and the differential operator is given by this Lu of x. L is the differential operator operating on the function u, that is given by this equation 1. P0 of x d square by dx square u of x, P1 of x d by dx of u of x, P2 of x u of x. This is Lu of x. Okay, and here these P0 of x, P1 of x, P2 of x, these are all the coefficients which are real and functions of x over the region of interest. Our interval is this, a less than or x less than or equal to a less than or equal to b. So this is the interval that we consider. So in that interval, we define this linear second order differential operator. And actually it is of this form, the form that we studied, d square y by dx square plus p of x dy by dx plus q of x y equal to 0. Here if I divide this entire equation by P0 of x, I will be getting P1 of x by P0 of x here, P2 of x by P0 of x here. So this P of x is P1 of x by P0 of x, and Q of x is, Q of x is P2 of x by P0 of x. Okay. So anyway, we are going to consider linear second order differential operator of this general form. So L is a differential operator that operates on U. Okay. And it is, what I want to tell you is this is of the form that we already studied. Okay. If we make such changes, if P of x is P1 of x by P0 of x, Q of x is P2 of x by P0 of x, we will be getting the same equation that we study. Okay. Now, as we said earlier, U Lu. Suppose I am taking inner product of U with Lu. Okay, so we have this U, Lu is this. So this is integral to be U of x, and Lu is this. Lu, it is this. D square U of x by dx square written as U double prime. This is written as U prime, and it is written here. So this is our U, Lu. And we have ULU, and that is given by this. Now we can split it into 3 terms. We have this integral U P0 U double prime dx. Here we have integral U P1 U prime dx. Here we have integral U P2 U dx. Okay, we split this. So the first term, if we integrate by parts, this is the first term. If we integrate it by parts, we have this. Okay. We write this in this form, and certain terms gets cancelled here. Okay, this term gets cancelled, so they get cancelled, and we are left with this minus U P0 prime U integral, limits a to b, integral a to b U P0 double prime dx. Okay. And from the second one, this term, this one we have obtained now. So the second one, integral a to b u p1 u prime dx, that is written here. Integration by parts, and you will be getting this. U p1 u limits a to b minus integral u p1 prime dx. Okay. So what we have is this lu. If we substitute for this first term from here and for this second term from here, you will be getting this ulu inner product of u with lu, that is given by u p1 minus p0 prime u. Okay, here we have p1 and here we have p0 prime minus p0 prime. So u p1 p0 prime u limits a to b integral a to b u p0 double prime minus u p1 prime plus p2. Okay. Now we define a linear operator which is adjoint of the L. Okay, we are defining L adjoint, LU. L is the adjoint operator, and that is given by this d square by dx square minus p0u minus d by dx of p1u then p2u. So this will be basically LU. Okay, this will be LU. Then we have a u here. So u LU or LUU we can say rather. So this L adjoint u, this is L adjoint u. As you apply the product rule and differentiate, okay, we will take first d by dx of p0u, then d by dx of that is written here, and certain terms will get cancelled, and we will have this p0u double prime 2 p0 prime. Okay, 2 p0 prime. Here we have p0 prime u prime. Here we have p0 prime u prime. So 2 p0 prime u prime. Then p1 prime u prime is here. So we can combine them, and we have this. Okay, so we get this equation. This is L adjoint u, and suppose p0 prime is equal to p1. P0 prime is equal to P1. This is an important criterion. P0 prime equal to P1. Then we have this will become P1. Okay, and here P0 double prime. If P0 prime is P1, P0 double prime will be P1 prime. So this will go, and we have this L double bar u equal to, L bar u equal to p0 u double prime, p1 u prime plus p2 u, which is LU itself. So L adjoint u, that is equal to LU, or L adjoint is equal to L. Okay, L adjoint is equal to L. Okay, so L adjoint, that is equal to L. That means this is self-adjoint. How it is self-adjoint? When P0 prime, that is equal to P1. Okay. So we have earlier seen that suppose we have to inner product of U with LU. Earlier we were talking about U and V. There can be U and U. So inner product of U with LU, which we know that is by this notation, it is L adjoint U, and if this L adjoint is L, this will be LU U. Okay, LU U. So we have this L adjoint equal to L. That means U inner product of LU that is equal to inner product of LU with U. Actually it is L adjoint, but since L adjoint is L, it is inner product of LU with the U. The condition is P0 prime x is equal to P1 of x. So when this condition is satisfied, okay, P0 prime x equal to P1 of x, when this condition is satisfied, the L adjoint U that is equal to LU, that is d by dx of P of x, du by dx plus Q of x, U of x. Because our original equation is this. What is the original equation? P0 of x P0 of U double prime plus P1 U prime plus P2 U that is equal to 0. So if P0 prime is equal to P1, I can write this as d by dx of P du by dx. Okay. When you differentiate this, we will have first P d square U by dx square. Okay. So we have this P0. Then the next term will be P prime, okay, P prime du by dx, which is P prime is our P1, plus that P2 term will be there. Okay, P2 term will also, that will be there. So we say if L adjoint is equal to LU, where that L adjoint as we define. Okay, we have seen the definition of L adjoint. L adjoint U that is equal to LU, and your differential equation can be written in this form. Okay, and the operator is said to be self-adjoint. Okay, so here P0 of x is P of x, P2 of x, that is the Q of x. We have taken P2 of x as the Q of x in our original definition for the differential operator. Okay. So we have seen the self-adjoint differential operator, and for a differential operator to be self-adjoint, we have seen the important criterion P0 prime of x that is equal to P1 of x. Now we have so far studied many differential equations. One is the Legendre equation. This is the Legendre equation. For the Legendre equation, we can very easily see here we have 1 minus x square, that is our P0 of x. Okay, that is our P0 of x, and here we have P1 of x, that is minus 2x. Clearly, the P1 is P0 prime of x. Okay, because P0 of x is what? 1 minus x square. So P1 of x is P0 prime of x. So for this, clearly this is a self-adjoint differential operator, and if I take the linear harmonic oscillator, here also we can see P0 of x, that is 1, and what is P1 of x, that is 0. Okay. So clearly P1 of x is P0 x prime. And these two differential equations are clearly self-adjoint differential equations. These two are self-adjoint. But what about these equations? For example, if I take Bessel equation, we know the P0 of x, that is x square. What about P1 of x, that is x? So it should be 2x for this to be a self-adjoint. So this is not a self-adjoint differential equation. Lager equation is not a self-adjoint differential equation. This one, Chebyshev equation, is not a self-adjoint differential equation. This one is also not a self-adjoint differential equation because here we have P0 of x as 1 and P1 of x should be 0, but we are getting it as minus 2x. So this, in this set, only the Legendre and simple harmonic oscillator is self-adjoint differential equation. Okay, so is there a way to transform a non-self-adjoint differential equation? We have a non-self-adjoint differential operator with us. Can we convert this into self-adjoint form? Okay, so we have Lu of x, P0 u double prime, P1 of P1 u1 x, P2u with P0 prime not equal to P1. Okay, it's possible to transform. So it's possible to transform this into self-adjoint form if we multiply this differential operator by this 1 by P0 of x exponential integral x, only upper limit there, P1 of t by P0 of t into dt. So if we multiply this operator by 1 by P0 of x exponential integral x P1 of t by P0 of t dt. Okay, we have this self-adjoint differential operator. So a non-self-adjoint one can be transformed into self-adjoint one. That we can prove here. Okay, that we can prove here. Suppose I am multiplying the equation suppose I am multiplying this equation by what? Integral. We are multiplying this Lu of x by this 1 by P0 of x exponential integral x P1 of t by P0 of t into dt Lu of x. As you multiply, you will get this 1 by P0 of x, this first term, second term, you will get this, third term, it will be this. Here you can cancel this P0 of x. Okay. So, this is equal to this exponential, P0 of x gets cancelled, so we have exponential integral x P1 of t by P0 of t dt u double prime. Then we have P1 by P0 exponential integral x P1 of t by P0 t dt u prime. Then we have this P2 of x by P0 of x exponential integral x P1 of t by P0 of t dt u. Okay. So when we look at these two terms, it can be by product rule, we can write it like this. D by dx of exponential this, and you will be getting these two terms. Okay, if I take d by dx of this, I will be getting this. And so clearly this is in the self-adjoint form because we have d by dx of this, then this term, so we have this differential equation in self-adjoint form. So what we did is we multiplied the entire equation, the entire differential equation that was multiplied. This is the differential equation that was multiplied with this 1 by P0 of x exponential integral x P1 of t by P0 of t dt. I multiplied. And I am getting what? I am getting this, a self-adjoint form. Okay, and we will illustrate it by considering the Bessel equation. Suppose we have the Bessel equation with us. Bessel equation is this: x square y double prime x y prime x square minus n square y equal to 0. Clearly, this is not self-adjoint because we should have got 2x here to make it self-adjoint. So if we multiply this entire equation with this 1 by P0 of x exponential integral x p1 of t by p0 of t into dt. Here p0 of x is x square. Clearly it's x square. P1 of x is x. So 1 by p0 of x is 1 by x square. Exponential p1 of t. P1 of x is x, so p1 of t is t. P0 of t is p0 of x is x square, so p0 of t is t square dt. We integrate and apply the limit x, and we have 1 by x square log x here, because we will be getting dt by dt, dt by t, and we have this x by x square, so we will be getting 1 by x. So if I multiply the factor that I have to multiply, the Bessel equation is 1 by x. If I multiply with 1 by x, I should be getting a Bessel equation in self-adjoint form. So if I multiply with 1 by x, I will be getting here x y double prime plus y prime plus x square minus n square by x y equals 0. Clearly this is self-adjoint. See, here p0 of x is x, p1 of x is 1, so clearly self-adjoint. And the self-adjoint form is this. Okay, d by dx of x dy by dx plus x square minus n square by x y, that is equal to 0. So what we have seen is Bessel equation, which is in non-self-adjoint form, has been transformed into self-adjoint form. And we can do this for Lager. Lager is not self-adjoint, and we do the same thing, and we see the term that we have to multiply is x e to the power minus x. Okay, and if I multiply with x e to the power minus x, I can obtain the self-adjoint form of the Lager equation. And for the Hermite, we can see the term that we have to multiply is exponential minus x square by the same method, and we can obtain the self-adjoint form of the Hermite equation. So any non-self-adjoint differential equation can be converted into a self-adjoint differential equation. Okay.